In this work, we talk about the design of task-oriented conversational agents or chatbots. You must have seen hundreds of articles outlining how chatbots are going to revolutionize the customer support industry. In this work, we go deeper into how such agents are designed. Meet Tanya. She designs chatbots for the enterprise by laying out a dialogue graph, or tree, that captures the different conversational flows she wants the chatbot to be able to support. Since enterprise applications must guarantee good customer experience, end-to-end learning-based approaches that offer no control over the deployed behavior of the bot are not enough. Instead, Tanya has to lay out larger and larger dialogue graphs, and the design process soon becomes intractable. As a result, any chatbot of sufficient complexity remains out of scope for the state-of-the-art design practices. In recent work, the planning community looked at the bot design process and offered a declarative solution to this problem in the form of a tool called D3WA. Now, Tanya gets to write a higher-level specification for the bot and can let a planner build the graph for them automatically. Tanya begins by putting herself in the shoes of the bot and writes down the variables that describe its world and the capabilities or actions available to it to change the state of the world. For example, if we are building a pizza delivery bot, the customer's payment details would be captured in a variable, while the ability to ask for them or to ping an API and put in the order are capabilities the bot has available to it. We consider three kinds of actions: dialogue or speech actions to interact with the user, and internal actions such as logic actions to make inferences on the state of the world, and cloud functions to make system calls. At the heart of the declarative specification of these actions is a structure, all too familiar to the planning community. Each action is defined in terms of a set of needs or preconditions that are required for an action to execute. And a set of outcomes. Each outcome models a set of updates to the world. Tanya envisages the different possible outcomes that can happen when an action is done. Only one of them materializes at the time of execution. For example, when the bot asks the user for their name, either they can respond with their name or say something completely different. Similarly, if the bot is trying to ping an API, either it may get the required response or it might hit a 404 error. These possibilities are defined as outcomes. In the background, a non-deterministic planner stitches these outcomes together to generate the dialogue tree. Tanya can now visualize and debug the tree and talk to the generated bot. The details of the dialogue specification overlaid on these planning components are out of scope for this presentation. But the key takeaway from this setup is that Tanya is able to achieve exponential scale-up of the sophistication of the chatbots by adopting the declarative paradigm. However, it turns out that Tanya, who is accustomed to the current way of designing dialogue trees, finds it very hard to grasp the declarative mental model. In particular, since this approach has handed off the construction of the tree to an automated planner, Tanya must be able to anticipate the imperative consequences of their declarative specification in order to be able to understand and trust the behavior of the deployed bot. In the early deployments of the D3WA tool for the declarative design of conversational agents proposed in the existing literature, Tanya is often stuck with questions of unsolvable specifications or solutions that do not match their expectations. This is where we come in. In this paper, we propose an explainable extension to this tool with the aim of making Tanya more self-sufficient. In particular, we want the tool to be able to answer these questions from Tanya without requiring help from planning experts while constructing the declarative specification. The way we propose to do this is by surfacing the issues in the model in abstractions of the current specification so that Tanya can fix those issues in much simpler form without having to plow through large specifications in search of a fix. Let's now head over to our tool to see this in action. We are going to design a conversation with a bot, helping in the inspection and logging of the status of the various parts of a car. The interesting part here is the possibility of an initiative switch during the conversation. Either the user can go through all the parts by themselves or hand over control to the bot to guide them, or a combination of both. Let's see how the specification of this bot looks like. The variables on the left log the status of the car parts and messages to and from the user. The specification includes a catch-all dialogue action to respond to the user when they have initiative and a set of actions to ask the user for information when the bot has initiative. There is one outcome in each action that switches initiative based on what the user has said, while the other outcomes update the state of the inspection by logging the correct variables based on the user utterances. Tanya hits compile and is faced with an error. The planner cannot find a solution to this model. Clearly, it's a daunting task now to go through the specification to identify the cause of the failure. However, she can use the in-house debugging feature to load up a minimal abstraction of the model that is also unsolvable. Unless the problem is solvable in the abstraction, it won't be in the full model either. Tanya can thus first fix the problem here and then translate that to the full specification. As you might notice, a bunch of the variables has disappeared and most of the actions are now empty. From the projected variables, it seems that there is a problem with the status of the spark plugs. It never appears in the catch-all action that drives the user initiative, as evident from the lack of highlight. Tanya goes into the catch-all action and notices that the update for the spark plugs is missing and fills them in. Now the minimal projection is solvable. Keep in mind how small this problem is from this generated dialog tree on the solvable projection. Tanya toggles back to the full specification and puts in the same fix. We have a solvable specification now, and the dialog tree looks like this. Notice how much compression we got out of the minimal projection to aid in the debugging. However, something still doesn't look right. Upon close inspection of the graph, Tanya notices that all dialog flows, where the bot drives the conversation, are missing. She lays out a foil to test, and indeed that turns out to be the case. She now queries the system for an explanation on why this is the case. The system again generates a minimal abstraction, this time using the foil as a hard constraint to be preserved in the generated dialog tree. On the right, we see a possible completion of the foil, laid out with diagnostic information as to why it fails. This foil is generated from a maximal solvable abstraction and includes an unachievable landmark that the user initiative cannot be flipped as a specific directive for Tanya to take into account to make her foil part of the solution. Tanya now heads over to the projected specification again. Everything else other than the initiative switch has been projected away now, so there is a clear issue here. Since the initiative never switches away from the catch-all action, Tanya once again inspects this action and indeed finds that the update to switch the initiative, when the user asks for it, is missing. The fix promptly generates a solvable minimal projection. Upon propagating this fix to the main specification again, we end up with the new dialog tree. This continues until Tanya is happy with the generated bot. We tested our system on 3 domains derived from earlier literature on declarative domains for generating assistant. We were interested in evaluating the compression achieved by the methods and the difference between the maximal solvable model used to derive debugging information and the minimal abstraction. We will skip the discussion on the computational characteristics since that is not the focus of the paper. In terms of the size of the resultant minimal models, which we measured in terms of the number of model components, we see that the user is exposed to much smaller domain files. For example, in the case of credit card domain, while the original model contained 2K components, the resultant minimal abstraction only contained 5 components. Now let us compare this against the maximal abstractions we generated for extracting debugging information like exemplary plans, whose failures on the minimal model are presented to the user. As you can see, it is extracted from much more complex domains than the one that is finally exposed to the designer. This is what we would desire, as it would allow us to test the minimal model on behaviors closer to what the designer would have expected. So in summary, we saw how tools from the explainable AI planning community can be adopted to help in the model acquisition task, particularly in the context of a tool for the declarative design of dialogue agents. Thanks for watching our demo.